Hello everyone, my name is Varnika and today I will be discussing facial recognition technology using Fourier Transform. This technology is widely used in smartphones, surveillance systems, and social media. We will explore how the Fourier Transform, a mathematical tool, enhances facial recognition systems by transforming image into a set of frequency pattern. So let's begin by understanding what facial recognition technology is and why it's important. So facial recognition technology identifies or verifies a person by analyzing the geometry of their facial features. The process includes face detection, locating the face within the image. Second, feature extraction, identifying the characteristics like the distance between the eyes or the shape of the jawline. Third, matching, comparing these extracted features with stored data to find a match. Applications of facial recognition include unlocking phones, enhancing security at airports, and tagging people on social media. It's important because it brings convenience and security to our day lives. Now, what is the Fourier transform? The Fourier transform converts data from the spatial domain, such as an image, into the frequency domain. For images, we use the 2D Fourier transform. It's represented by the equation as you can see here. Here, the fxy represents the original image in the spatial domain. FUV represents the image in the frequency domain, and U and V are the frequency components. So, this transformation breaks down the image into a combination of sinusoidal waves with different frequencies, making it easier to analyze. Now you can see this, the whole process, how it is done exactly. We upload the image of our face, and then it analyze the appearance features and convert it into the geometric features. So why we use Fourier transform in facial recognition? So let's understand that. First, extracting frequency pattern. It highlights unique facial features by focusing on patterns found in the frequency domain. Second, it is resistant to noise. Like it filters out irrelevant details, making the system robust even in low quality or noisy images. Third, rotation and scale invariance. Like it remains stable when the face is slightly rotated or resized. For your example, we can take example like when a face image is converted into frequency domain. Dominant frequencies can help identify the face while others are ignored. Now, how it works, what is the actual process of facial recognition using the Fourier transform? Now, let's walk through the process step by step. First, it is image acquisition. So, in this, we start by capturing an image through a camera or video frame. The image is usually in RGB format. Second, it is pre-processing. In the pre-processing, we convert the image to grayscale to reduce the complexity. Then we normalize the image to handle brightness or contrast variations. And then the image function in this step can be written as fxy, where x and y are the spatial coordinates and the pixel intensities are normalized. Third, applying the Fourier transform. The 2D Fourier transform is applied, converting the image to the frequency domain. Like you can see the equation here. Now the image is expressed as the combination of frequency component. In this particular equation, the image is expressed as a combination of frequency components. Now, step 4, it is filtering. So in step 4, we apply filters to retain or suppress certain frequency ranges. The filtered frequency domain image is represented by HUV. So where HUV is the filter function that focuses on the most important frequencies. Now, step 5, it is inverse Fourier transform. As you can see, it is completely optional. Like, if needed, we can use the inverse Fourier transform to convert the image back to the spatial domain after filtering. So, you can see the equation here. Now, step 6, feature extraction. Key facial features such as the distance between the eyes or the shape of the nose are extracted and stored as a feature vector. So here is the feature vector for this. V is equals to V1, V2 up to till Vn. Each Vi represents a frequency component characteristic of the face. Step 7, matching. The feature vector from the current image is compared to stored vectors using a similarity metric such as Euclidean distance or cosine similarity, as you can see the formula of the similarity here. And the last step is decision. Based on the similarity score, the system either recognizes the face or rejects it completely. Like you can see, high similarity score, the system identifies the person as a match, and low similarity score, the system does not recognize the person. Now, example of the process. So let's assume an image of a face is taken from a surveillance camera. So the system then analyzes the low and high frequencies, and the extracted frequency patterns are compared to the database, and the similarity score is calculated, and if it crosses a set threshold, then the person is recognized, otherwise the person rejects it. So it is also that, like, let's look at a practical example. Suppose a surveillance camera captures an image of the face. This image is processed using the Fourier transform, which breaks it down into its frequency components. High frequencies highlight sharp features like the eyes and eyebrows, while the low frequency captures smoother area like the cheeks. So equation for visualizing frequencies is written here. So the system then compares these frequency pattern with those in its database. If the similarity score crosses a set threshold, then the face is recognized. Now the last one is challenges and limitation. Although Fourier transform is powerful, it comes with some challenges. High computational cost. Processing large images with Fourier transform can be resource intensive. Sensitivity to shift. The transform might not work effectively if the face is slightly off center. Third, handling diverse faces. Diverse skin tones, facial shapes, or age groups can be difficult to manage using only frequency based information. So, to overcome these issues, we can use hybrid approaches combining Fourier transform with machine learning technologies like convolutional neural networks, CNNs. And at last, it is the conclusion. In conclusion, we can say the Fourier transform plays a key role in facial recognition by focusing on important frequency patterns. This approach helps handle challenges like lighting variations, noise, and slight rotations, leading to more accurate results. In the future, combining Fourier transform with advanced techniques like deep learning could further enhance the performance of facial recognition systems. Thank you for your attention. I hope this presentation provided valuable insights into the role of Fourier transform in facial recognition. Thank you.